A 0.5 kilogram object rotates freely in a vertical circle at the end of a string of length 2 meters. As the object passes through point P at the top, the tension in the string is 20 newtons. So we're going to start by drawing the free body diagram for the object when it's at the top and at the bottom. So in both cases, it has the gravitational force pointing downward, and the gravitational force is the same for both of them. When it is at the top, it has a tension force pointing down, since the string is in the downward direction, and when it's at the bottom, it has a tension force pointing in the upward direction. And then I'll also add on the centripetal acceleration as the separate arrow. When it's at the top, the centripetal acceleration is pointing downward toward the center of the circle. When it's at the bottom, the centripetal acceleration is in the upward direction, still pointing toward the center of the circle. Part B, calculate the speed of the object at point P. So let's take the free body diagram from point P and go ahead and write out Newton's second law for it. So we're going to make the downward direction positive, since that's the way the acceleration is pointing. So positive and negative is upward. The net force in the y direction is equal to, I'll try to make that look like a y and not a g. Net force in the y direction is equal to mass times centripetal acceleration. And in the y direction, we have two forces pointing downward, so they're both positive, Ft plus Fg, and that's equal to mv squared over r is the centripetal acceleration. And I can go ahead and replace that Fg, just replace that with m times g. So Ft plus m times g is equal to mv squared over r. We know everything in this formula except for the v, which is what we're looking for. So let's just do a full rearrangement to get v by itself. So we have the Ft plus mg. We first want to multiply both sides by r to cancel out that r in the denominator. Then we want to divide both sides by m to cancel out the m in the numerator, and then just square root of 5 both sides, and that will give you the value of the v. So if everything is plugged in correctly, let's go ahead and put the numbers in. The radius was 2, the tension at the top was 20, plus the mass, which was 0.5, so 0.5 times 10 is 5, divided by 0.5, and let's just work through this without using a calculator. So we have 2 times 25, which is 50. 50 divided by 0.5 is going to double it, so now it's 100, and the square root of 100 is 10 meters per second. Part C, calculate the increase in kinetic energy as it moves from point P to point Q. So since it is changing height as it's going from the top to the bottom, that means it's having a decrease in gravitational energy. So that decrease in gravitational energy is going to be accompanied by a corresponding increase in the kinetic energy, since the energy is conserved here. The only two forces acting on the object, if you look back at the original diagrams, are the gravitational force and the tension. The gravitational force is a conservative force, so that's not going to affect the total energy. The tension force is a non-conservative force, but remember, for objects in circular motion, the tension, in this case the tension, is always perpendicular to the displacement of the object. So at the top point, the object is moving horizontally, but the tension is in the downward direction. Bottom point is moving horizontally, but the tension is in the upward direction. At any point, they are perpendicular, so the work done by tension at any point along the circle is 0. So there is a non-conservative force here, but the work done by that non-conservative force is 0, so the energy, the mechanical energy, will be conserved. So if the mechanical energy is conserved, as it's losing potential energy by going from the top to the bottom, it's going to be gaining kinetic energy. So all we have to do for this one, it's very simple, is to say that the increase in kinetic energy is going to be equal to the decrease in the gravitational potential energy. So how much did the gravitational potential energy go down by? Well, it went down by mgh, where m was the 0.5, the g was the 10, and the h from here down to here is the diameter of the circle, which is 4. So we have 0.5 times 10, which is 5. 5 times 4 is equal to 20 joules. Part D, let's calculate the tension in the string as the object passes through point Q, the lowest point on the circle. So let's just go ahead and set up conservation of energy to figure out what is the actual speed at that point. The initial energy, mechanical energy, is equal to the final mechanical energy. So we'll say Ki plus Ui is equal to Kf plus UF. At the highest point, it is moving, so it has kinetic energy, and it does have gravitational energy. At the lowest point, it's moving, so it has kinetic energy. But let's just define that lowest point as the arbitrary reference point for potential energy. So if we just say that this red line right here represents the 0 point for potential energy, then we can just get rid of the UF from the equation. So we can now say, let's plug in the formulas, and since we're only dealing with kinetic and gravitational energy, we know that the masses will cancel out. So I'm just going to plug in the formulas with the masses already gone. So we'll have 1/2 v squared initial plus g h initial is equal to 1/2 v squared final. Now we need to figure out what is the speed at the bottom in order to get the tension, because once we have the speed, we can do something similar to what we did up here, but to calculate the up here, we were given the tension, and we calculated the speed. Now at the bottom, we'd know the speed, we would just have to calculate the tension. So let's rearrange this equation to get the V final, the speed at the bottom, by itself. We're going to multiply everything by 2 to get rid of the 1/2. So multiplying everything by 2, this will be gone, this will be gone, and this term will have a factor of 2 in front of it. Now this equation may look familiar. It's one of the kinematics equations. If you notice, you have the Vf squared is equal to V initial squared, or we use VO squared, plus 2a delta y. That's very similar to what we have right here. In fact, that's where that last kinematics equation was derived from, was from using conservation of energy. So anyway, back to this problem. Let's go ahead and solve for the Vf. So that means that Vf will be equal to the square root of V initial squared. The V initial is the speed at the highest point, which was 10. 10 squared plus 2gh. So 2 times 10 times the 4, the diameter of the circle, which will give you the square root of, we have 100 plus the 2 times 10 times 4 is 80. So this is going to be the square root of 180. And I'm just going to leave it in that form right now, even though that can be broken down a little bit or turned into a decimal form. We'll leave this right here. And the reason is because in the next step, when we go back to writing Newton's laws, since AC depends on a V squared, this is the square root of V. So we can basically just say that V squared, the Vf squared, is equal to 180. So it wasn't really even need to take the square root of everything when you're dealing with problems like this. Okay, so we are still working on part D. that was only like the halfway point, really. Let's keep on going with it. We're trying to find the tension at point Q, so we've got to use that second free body diagram. And for that one, we're going to define upward as the positive direction and downward as the negative direction. So the net force in the y direction equals MAC. And the net force there is equal to, we have the upward force of tension, the downward force of gravity. So we'll say Ft minus, and I'll just write gravity as m times g, is equal to mb squared over r, and then just bring this mg to the other side. That gives you Ft equals mv squared over r plus mg. The m was 0.5, the v squared was 180. The r, now this is just the radius of the circle, not the diameter, is 2 plus 0.5 times 10, which is 5. And what this simplifies to is you have 0.5 times 180, which is 90. 90 divided by 2 is 45. 45 plus 5 gives you the 50. So 50 newtons of tension at when the object passes through point Q. And for part E, determine the work done by each force acting on the object as it moves from point P to point Q. Well, there's only two forces on it, so we just need to calculate the work done by the tension force and the work done by the gravitational force. We already know the work done by the tension force is 0, since it's in circular motion, and the inward pointing force always does 0 work in circular motion, since the force and displacement are always perpendicular to each other. And then the work done by the gravitational force, we've actually already calculated this, because you may remember that the net work done on an object is equal to the change in kinetic energy. And in this case, the gravitational force is the only force doing work on the object, so the net work is equal to the work done by gravity. And we calculated the change in kinetic energy back in part C, which was 20 joules.